In this video, we are going to take a deep dive at the modular arithmetic. Okay. So in the previous video, I have skipped some mathematical steps. If you are a shrewd listener, you would have observed that initially I said this Z5, the 0, 1, 2, 3 and 4, this set, here the numbers, they are not actually integers. I mentioned that they represent another set. So that's why I put a dash above them. Okay. We will be actually working with integers. In the SCP-26K1 source code, we will be doing integer additions, multiplications, and so on. But we will round them up. We will only care about the remainders, right? So I will explain the steps, the mathematical steps that I did not show in the previous video here. If A is congruent to, let's say 2 mod 5 and B is congruent to 3 mod 5. So here this A and B denotes a single integer. The thing is, A could be any number which satisfies this condition. It could be a 2, a 7, a 12, a 17 and so on. Right? It could even be the negative numbers like negative 3, negative 8 and so on. Similarly, the same for B. But when we say A plus B, right, what is the question that we are asking is, if we take any number which gives a remainder 2 when divided by 5 and we take any number which gives a remainder 3 when divided by 5, whether it gives 2 plus 3 is 5, 5 is divisible by 5, so we will put 0 here. Whether the resultant actually belongs to this set denoted by the symbol 0. That's the question that we are asking. Okay. And it is very straightforward to verify. Because any number A which satisfies this equation should be of the form A is equal to, it's equal to some quotient Q. This Q could be any integer, positive or negative, times 5 plus 2. Similarly, B could be, let's say here it is Q1, it's Q2. Okay, Q2 times 5 plus 3. So when we are adding A plus B, here we are actually adding both of them together. We can take 5 common from both of these terms and we can write Q1 plus Q2 times 5 plus 5. The resultant can be written in this form, 5 into Q1 plus Q2 plus 1. So this Q1 is an integer, Q2 is an integer and 1 is also an integer. So the sum of all these three terms will again be an integer. So A plus B has the form of 5 times some integer, which means A plus B is indeed divisible by 5 and hence it is 0. So here you can prove that using the same steps which I have demonstrated. You can prove for any arbitrary A which is congruent to R1 mod n could also be arbitrary, right? And B congruent to R2 mod n, A plus B will always be congruent to R1 plus R2. I'm going to denote, use the modular symbol. Like if you are in programming, you know that the percentage is actually going to take the remainder. Okay, because R1 plus R2 can in fact overflow n, as like we have seen in the case of 5. Like take 3 plus 4, it is equal to 7, it overflows 5, so we will only take the remainder. Okay, we will only take the remainder 2. So similarly, R1 plus R2 can also overflow, but we are only interested in the remainders. Okay, and we can write them in this form. For any A and B, for an arbitrary n, which gives this remainder R1 and R2, we will be able to show that this is true. You can in fact verify this using the exact same steps as I have demonstrated here. Similarly, you can also say that A times B will be congruent to R1 times R2 mod n, like just a remainder of R1 times R2 and whole mod, and you can in fact write them in this form as well. Okay, so here multiplication symbol. All right. I will give a demonstration for multiplication with the example of 5 again. Let's say if A is congruent to 3 mod 5 and B is congruent to 4 mod 5, which means, we are asking the question, right? We are asking the question here whether A times B is congruent to 3 times 4 is what? 12. 12 is 2 mod 5. We are asking this question whether this is true. In fact, we can verify that by simply rewriting this equation as A is equal to some q1 times 5 plus 3 and B is equal to some q2, some other different integer, right? Doesn't have to be the same because A and B could be any other numbers, times 5 plus 4. Okay, and we do A times B. So this is like multiplication, a little bit complicated, but we can in fact do that. Okay, so we will multiply these terms one by one, right? So q1, now I'm going to multiply using this term against B. So I can write q1 times 5 into q2 q2 5, okay, plus q1 and this one I multiplied. Now I'm multiplying with this one. Okay, so 5 into 4 is 20. So I'm going to write 20 times q1. Like, I don't want to write that. Okay, let me just write 5 into 4 into q1. Okay, now 3 has to be multiplied with both these terms, plus 3 into q2 into 5 plus 3 into 4. Okay, so when we are actually doing the remainder calculation, if you can observe, right, so once again we can take a single 5 common from this term. Okay, we can take a 5 common out of this term and this term. So we can combine these three together and I can simply write some integer k times 5. So this k could be whatever the term that we get after taking 5 common from all these three terms, and we can write like okay, so that's that. For that alone I use a different thing, and for this we can simply write 12. Okay, 3 times 4, and 12 could be written in this form, right? So k times 5 plus 10 plus 2, because I just want to like factor out all the terms which are divisible by 5, because we want the remainder to be less than 5, right? Or positive integers to be less than 5. So this we can write as k plus 2, because 10 is actually 5 times 2 into 5 plus 2. So we don't even need to do anything with these quotients. We can simply ignore all the terms of the quotients because we have this multiplication by 5. Since we consider that number 5 as 0 when we are talking about mod 5, we can simply ignore all these terms, and it is enough for us to only work with the remainders, because 3 times 4, that is the only calculation we need to do, and we have to be careful about the overflow because it overflows greater than 5, right? So we just have to remove the overflow and we get the result that we want. Okay, so that's why this video is optional, because in order to actually understand the arithmetic, you don't have to do this. But if you are inquisitive, I have shown you how to do this. Even for the addition, if you observe, we don't even have to worry about these q1 and q2 terms, because we know that these two terms are actually divisible by 5. I can just simply ignore them. All right. Yeah. I hope this helps you to not be afraid about the math and read all the theorems related to this signature schemes which are used in the Bitcoin, because there are like several claims. If you go and read bit 340, okay, so there will be a statement that this Schnorr signature has a proven security, right? So they will mention that ECDSA scheme, which was prior to Schnorr signature, does not have a provable security. Okay, if you go and read those papers, they have linked a paper there. You will encounter these kind of like scary looking math terms, okay, and symbols, but you don't have to fear them, right? You can just, if you are careful enough and patient enough, you can in fact understand those as well.